let's do a little bit more complicated problem where we're going to solve for the equilibrium constant, given some information about equilibrium concentrations. So anytime you're looking at the relationship between equilibrium concentrations and the constant Kc, then you're going to set up a Rice table, which I've already started. First reaction, and then the initial. We were given these initial concentrations, and we assume we're starting with 0 here. And then on this next one, on the change, focus only on your x's and using the reaction to come up with the relationships. And I'm just going to, this is where we use these coefficients. So I'm going to say minus x here. There's no coefficient, so I just use x. My other reactant, no coefficient, so I just say minus x. But then when I get to C, I have a 2. And because if x of this reacts and x of that reacts, I'll get 2x of this. So I'll say plus 2x here. Some people draw a line right here because on this next part, you are essentially adding these two rows. And from there I can look at, let's look at what we have, because we do have the equilibrium concentration of our product. And so right there that tells us we know what 2x is. 2x is this number. By the way, when you start writing this, it's really easy to confuse these x's in the algebra with this x. So kind of try to make sure you're writing them different sizes or something so that that doesn't get messed up. But anyway, if we know that, then we know what x is, don't we? So in other words, and if we know what x is, we know what these concentrations are as well. So I'm going to not plug those in right away. Let's see what else we might want to do. So our whole goal was to find Kc. And let's go ahead and write that expression. Product, hydroiodic acid. And I'm squaring that because, oh, there it is right there, because the coefficient there, so that coefficient is used for different things. It's used for this too, but remember when we write our expression, it's an exponent. Then these don't, there's no coefficient on these, so I don't have anything there. Okay, so that's my equilibrium coefficient expression. But we said that because we know x, we can find all of these concentrations. And I didn't write it here, but these are the equilibrium concentrations that I need right here. So I'm going to plug those in to Kc, and I have x, so I can plug x in as well. So let me do that, and then I'll point out what I did. Let's see. Okay, let me point out where all these numbers came from. This number was 2x. This number is the 1.00. It's written kind of funny, but it's what it is. Okay, and again, those values I got from this. That's why I plugged in what I did there. And if I plug in all of those numbers, and then as far as units go, we know that all of these had units of molarity, but remember, we just kind of ignore that because someday we'll be using activity coefficients that don't have a unit. And anyway, so Kc doesn't have a unit, but when we think about sig figs, look at the sig figs that were given. And when we say that, we're talking about the number of sig figs. And originally we had 3 sig figs in our concentrations, so we'll go to 3 here. So when you're getting Kc, you use kind of the multiply add rule. You go by how many you had, or multiply divide rule, how many you had. It's when you are going for the final concentrations and you're doing the very end add subtract that you start using the rule where you line them up, cut them off. Okay, so we got our Kc.